Welcome back to another episode of Peep and EIP, an EIP focused series, where we are trying to understand details of an improvement proposal and why that is needed for Ethereum network. Today we are going to learn about EIP-2935, save historical block hashes in state. And our guest is Tomasz Stanczak, who is also the founder and CTO of Nethermind. Tomasz, great to have you on the show. Before getting into the proposal, let our audience know a little bit about yourself and how you joined the Ethereum community.
Sure. Yeah. Hi. Thank you for the intro. I've been working on Nethermind client for the last 3 years as a developer, and because of that, obviously, I have interest in the changes to the protocol. That's how I ended up on some of the calls, listening, and after a while, I probably started talking a bit. And 2935 is in particular one EIP that I'm really interested in, one that I think that can bring some simple yet powerful improvements. So if we're fine with this intro, then I'll be happy to introduce everyone to the EIP. Okay, great, thank you so much. So as you see the name, save historical block hashes in state. So you may know that currently we have, okay, all right, so saving historical block hashes in state. As you know, we currently have an opcode that's called block hash, which allows the virtual machine to query any block hash up to 256 block hashes before. And this block hash nowadays is used probably for some verification of headers for the recent events, but also by some is used for the random number generators. Maybe not the best solution, but by many just treat it as the simplest one for some non-critical situations when you have to do some randomization. And EIP-2935 suggests something relatively simple. It defines the block hash storage address at this address, FFF with E at the end. Because we use, I believe, FFF, all Fs is a system account, and here we storage here. At this address, before every single block, before all the transactions in the block are executed, we plan to call a single S store at this address that you've seen in the previous slide, and we push a block hash there at the storage slot at the number of the block. So we can save the storage as block 12 million, for example, and the hash as the value in the storage. So the S store always takes address as the address of the contract and the index in the storage key value store, and the value will be a block hash of the parent block. So we don't do that in the given block because we don't know the hash yet. When we process the block, when we're verifying block, we don't know yet what the state root will be. We only calculate it after processing the block, which means we push the parent block hash to the state. And because of the way the storage is stored at the moment, you end up with Merkle root, whether it's physically on the disk, on the storage device, it doesn't matter, but it's important that you can construct proofs and you can get the storage root of that Merkle tree of all the block hashes. And you can use those proofs for any use cases in the future. And how we do that, so we extend the block hash opcode later for inclusion of any range requests beyond 256 blocks, all the way to the fork block for the EIP-2935. So if the fork for 2935 happens at 10,500,000, then we can ask about the block hash of that block, even in the block 11 million inside the EVM. So suddenly the block hash opcode is much more powerful and can be used in other situations. And also because of storing it in the state, instead of having this magical additional requirement for EVM to have access to the last 256 headers, which are really outside of the state in the way we see the state as world state of accounts and storages. So instead of this, we can just reach to the storage of the account. What are the use cases? and they can be collected from Discord channels, from the Ethereum magicians and ETH research. Generally, mostly we'll be talking about light client syncing, like fly client, less even. Stateless Ethereum, why? Because we need to build witness, and witness has a bit of difficulties with dealing with block hash opcode, because suddenly you have to include the block headers in the witness, which is not very convenient. Either you need to require all the stateless clients to actually keep that kind of state of last 256 headers always. And for blocks that would be from the past, you would have to request more and more headers to have this full verification. Or yeah, in this solution, when you have 2935, you can include the block hashes within the witness itself, because it's just treated as the storage, the same way as any other storage. Historical header verification. So whatever you can do now for the last 256 blocks with the header, you can do for anything from the past. So you can imagine suddenly being able within the EVM to start talking about the state of the account in the past. So you can imagine the questions like, if you can prove me that you've ever had on your account given balance of ETH, then I'll do something. Or if you can prove that you've ever been an owner of something in the past, then I can do something. So nowadays it's not possible because EVM has only access to the current state. If you can reach for any historical block, then you can provide a proof that is verifiable against the state root that's within the header. And you can provide the header as well, because you have a block hash, so you can verify if that header actually existed in the chain. And you can do that all from the EVM. And some of these questions are only related to the header. So for example, can you tell me what was the difficulty of the header from 1 million blocks ago? But the other ones can actually ask about historical state. And this is quite powerful. I mean, you can create lots of different products based on that. Where are the links? So 2935 link itself, if I send this presentation later, if it's shared, then you'll be able to just use those links for convenience. And there's also ETH research, which mostly discusses fly client, light client use cases. And there, EIP-2935 is suggested as one of the powerful solutions, a bit like a compromise between a perfect solution and a very slow solution. I mean, not compromise, really, like something in between, but much closer to the perfect solution, I think. There is an implementation done in Nethermind in one of the branches, so feel free to look at that code. I'll show it to you in a moment. Ethereum Magicians link. And this one, I believe, discusses a bit more the witness, and also compares the 2935 with the previous approaches to the same thing. 2935 generally is very clean and simple compared to previous solutions, previous suggestions. They're both authored, like both main suggestions, I think 210 and 2935 were suggested by Vitalik, but this 2935 was a bit of huge simplification over the previous approach. What's for the discussion based on the implementation that I'll show in a moment, whether the change in the block hash opcode should include the gas cost change to the S-load cost, because suddenly block hash becomes S-load, but it's only S-load for the very first transaction in the block, and later it can be cached, I guess. But if we have 256 blocks in the past, and if we don't create some additional structure for those, then it's really S-load on the storage. So it's a bit of a question. My preferred solution would be to introduce another opcode, potentially long block hash, that would cost more, because then we don't change the cost of the existing opcode suddenly from 20 to 5,000, or like 200, sorry, on the S-load, if it's repeated. And there is one more thing, because the current solution suggests to store the storage on the address that doesn't have the contract code. It creates a bit of maybe nothing very bad, but suddenly it's different than what we used to. There exists an address on the chain which has storage but has no bytecode. So my suggestion here is to deploy a bytecode at this address with a single stop instruction there. So 1 byte bytecode that can be used as a, okay, there is some contract there, so it's fine if there is storage. And that prevents the clients to have to handle some special cases when we have the touch dead accounts and remove the account, which is the remnant of the past of the cleaning of the accounts after the Shanghai attack. And that's it for the presentation. I'll show you the source code as well quickly. Can you see the source code? Yeah. It's not, it's literally source code. Never mind, I hope it's readable. I changed slightly the variables for you to read. There is also some kind of pseudocode at the specification. So generally depending on the 3 numbers, really, the current block number, the requested block number for the hash, and the transition block for EIP-2935, we define the behavior. So if we are within 256 blocks from the transition, then because we haven't filled yet all the historical block hashes that we could normally ask about with the block hash opcode as it is now. So we behave the same way as the block hash behaved before. So we have some kind of access to the block hashes for the last 256 blocks, and we ask about this requested block number. Later, if we are beyond this 256 transition period, then if we are asking about the block that is after 2935 transition block number, then and here is a suggestion of actually charging S-load cost on over the block hash and requesting from the storage cell of the block hash storage requested block number. We just read the storage cell and the storage from that storage cell. And this is the block hash that we return. And if we're asking about the block from before the fork, then we return 0 because we simply don't have it in storage. We know that we don't have in storage any blocks that were created before the transition, before the fork. And that's it really. So that's what it does. And there are some tests here, mostly for telling us how we should behave, whether we should use old style block hash or the new approach, depending on what's the transition block, what's the current number, what's the requested number. And this one tells us which behavior we should pick. So I can analyze it in details, but the opcode here is quite simple. So we just push the requested number. We call block hash, and then we load the store. We store in storage, and then we verify if after loading, we verify what was called, whether we called the block hash provider as it was in the past, or we read the storage cell. So this can be obviously different for different clients, the way it behaves, but these test cases can be easily used and adapted for different clients. Also, the clients will have to test the behavior at the transition boundary, so at the fork, of whether we start to save the block hashes in the storage before the block execution. So you can think of it, this is a bit like an additional 20,000 gas cost of storage before every single block, but it's not really 20,000 because we don't really read before saving, we just save straight away. So it's much cheaper operation than executing it in the virtual machine. Yeah, so that's about it, I guess. If there are any questions or maybe suggestions that I missed something that would be important to add here.
Sure. I'll jump in. First of all, thanks a bunch for showing the code. I think that's really, I think that really gives like a good sort of hands-on feel for what's going on with the EIP. Just a few maybe basic level questions. Maybe I'll try and zoom in on a thing or two. Does this affect full sync at all? If we're changing where the block headers are, should we see some kind of change in full sync? Also, to the best of my understanding, right now, full sync stores the last 256 blocks fully, which I see as the same number. Is that affected in some way by this?
So currently, both the full sync and fast sync will most likely download all the headers from Genesis, or at least from some hard-coded block header, but this is only if you trust that block header. So this EIP assumes that you no longer have to create some kind of external source of truth about what block hashes were there in the past. So clients that follow last protocol, the light client protocol as defined by Geth, may actually use it instead of checkpoints, I believe, for loading historical block hashes. As for the storage of all the block headers, it's around 8 gigs currently, I believe. Depending on the client implementation, downloading all the headers may take between 15 minutes and 2 hours, I believe. But this requires quite a powerful setup when you have lots of parallel connections. Any light clients that try to operate from very weak machines or from the browsers, potentially, they wouldn't really do that because downloading headers would be really like a networking nightmare for those. Yeah, I guess it answers your question in a way that these 256 headers, yes, they are currently downloaded and maintained by all the full sync, fast sync clients. As for the light clients, most likely they have to load much more headers than they would like to, just because of this block hash, potential block hash code. And also like the same for stateless clients as they would appear, you have a bit more pure verification of the block itself and the witness, because you don't have some externality to all your analysis. Does it answer your question?
I believe so. I mean, so full sync should remain the same thing, even with the change in how the headers are stored. And the fact that...
Yeah, so it remains the same in a way that you don't decrease the storage requirements of the full sync, but the benefit of not loading headers in full sync would be negligible, because if headers are 8 gigs or even less,
right,
and obviously the full sync will have 1 terabyte plus of data, then this wouldn't be really...
I didn't mean archive. I meant with archive,
sync,
you're over
full sync, yeah, full sync as you have full state. I mean, if you can think of approaches that we took at Nethermind, where we allow users to decide not to download historical headers, but we actually suggest not to follow that option, so it's not default. You can skip those. But then it's not super healthy for the network, because others cannot really ask you about the headers. We use it for beam sync, and in the beam sync case, I think this EIP would help as well, because it gives much easier. It enables much easier verification of the headers that you start from. You can start from very late headers instead of either hard-coded headers or even worse, Genesis, just by sampling from different other nodes on the network. Like the BeamSync then behaves a bit like Fly client in verification of the hashes, of the block hashes, but then it uses some state requests just to get state quickly. So you have everything together without downloading any big structure, whether these are headers or bodies or transactions or state.
Interesting. I mean, yeah, even on the full one, it's not archive, however large full sync is right now, which I think may depend on how much gets flushed onto actual storage. I mean, the 8 gigabytes of headers is still going to be negligible compared to whatever state's being stored on full.
Yeah, I think the full client in this most minimalistic form would be around between 60 and 300 gigabytes, depending on whether you include bodies and receipts.
Yeah.
So this 8 gigabytes of headers is like probably the most essential for security at the moment, and also a bit like least heavy part, because headers are just quite light. I mean, 512 bytes per header.
Mhm. I also wanted to zoom in on light clients a bit. I'll admit some of this is likely my own ignorance about how light clients function, but I was wondering if maybe you already started answering this in the answer to the last question, but maybe if you could talk about how this EIP would help light clients, as in what
So-
allows a light client to be so light?
Yeah, the light client usually, I mean, when we think about light client, it's something that should exist with minimalistic state, if possible, right? So something that syncs very fast because it doesn't really require everything to verify the full blocks potentially, or just something that is necessary for the block. So how can you execute a light client here? If you just want to execute a transaction, then you may potentially request just the proofs of your current balance for your account. So I believe that's how last protocol behaves. So you can connect, you download some kind of headers tree with the checkpoints that are stored on chain. And here it's a bit of like unpleasant thing that those checkpoints have to be pushed there by someone. So you have the external influence over what is truth and what's not. And then after you verify what's the longest chain, you can start asking about the proofs of some parts of the system. So like it could be, give me a proof of the account balance, and then I can create transaction based on that. So that's one of the approach with the light client. The beam sync is a bit like light client on top of the full sync fast sync. And the light clientness of beam sync is that it also downloads just the state that it needs for executing transactions and verify particular accounts, but it doesn't ask for proofs, but it literally asks about the physical representation of the state tree. And again, if those clients, the beam sync and less, are to execute very fast and with minimal storage, like with just proofs, so potentially with just a few hundred kilobytes or maybe even less of data, then we don't expect them to download 8 gigabytes, because while we were talking about 8 gigabytes being negligible in other cases, here it would be a huge part of any data interaction and downloads, like impossible to download in most light client scenarios, in many at least. If you have EIP-2935, then you kind of you are able to start sampling these different headers from different nodes on the network, and you can also, for the winner node, you can verify if those samples really exist to the chain. So you have like additional strength, additional force of verification.
I think it may have been missing. How does that avoid the need for headers? As in, before the light client needed to be able to verify headers, which was pulling it into the situation where we need the 8 gigabytes, which in a lot of the cases in the browser, mobile data, things like that, becomes like this huge burden. Now we can avoid the headers. Sorry.
In the past, it didn't need to download 8 gigabytes of headers, but it would use some kind of structure to avoid it. So the LESS protocol suggests us headers trees, like the Merkle trees of headers, something like that. It's called CHT. Hash headers tree, something headers tree, compact headers tree, whatever. But those structures are like not exactly natural, in a way that there are very strong, like some additional object introduced by protocol, and has to be pushed, like those hashes of those structures have to be pushed to some contract on chain ideally, or you can ask about those and collect some kind of Merkle proof verifications, but it's a bit awkward, just a bit. And you can avoid it here, for example, by knowing which was the header of the fork block, and then sampling different headers from different nodes. So like the way the fly client does. And then after you start requesting state from the longest chain, you can also verify those headers that you sampled if they're really on chain according to the longest header that you know. So I think like for light clients, maybe this is not. I mean, for fly clients, I believe this just simplifies some structures like and necessity of requesting more data. I think here I suggest you for the light client scenario to go to the F research, and there is a great discussion about it from Sina Mahmoudi, I believe, if I pronounce it right, and that's where it will be great to ask those questions. As for the witnesses, so obviously there you simply don't have to have those headers anymore because you can just include it in the state witness. And for anything DeFi or historical account scenarios, so this is just simply solved by having access from inside the virtual machine to the block hash.
I understand. And maybe just a last one from me. I'm not sure I understood you 100% right about when you were talking about stateless. In order to really leverage EIP-2935 for stateless, does that mean that there's also going to be another piece of information that would be being stored here, or was stateless also leveraging just the historical block hash itself?
So there'll be less information required, because imagine that you have a block nowadays or a transaction that invokes block hash 256 times for every single number available to ask about. So then alongside the block witness, you have to include also those hashes. And now the way the block witness is delivered is that you can, so you can either provide it in the form of proofs, which might be a bit inefficient, or in a way where you actually compress it and you hash it and include it in the headers. In the second scenario, you have just the ability of adding those 256 headers as part of the witness, but the verification of those headers is, I mean, like, it would have to be included in the header hash in a way. Here you don't have to have any additional complexity into the construction of witness. So whether that's super important is another question. I mean, like, it just makes the block witness more unified. It's the block hashes belong to the state witness. Like if you call block hash, then what you do now, you have to have some external structure of headers. What you will do after 2935, you'll be just calling the storage access of the state. So it will be like any storage access, which means that it conforms with the standard operations that you do for the witness construction.
As in, the call is going to be the exact same. It could be depending on how stateless develops that we'll have different styles of information that might be stored there, but it's always going to be stored at the same place.
For the witness, or so like this will be part of the state if it's 2935, whether we'll have other parts of information in the witness and block witness. So we want to make it as small as possible. Obviously, I mean, the big questions about the witness of the block are the code merkleization. So how to include the just parts of the code that you access when you execute smart contracts to avoid some kind of attacks on witness sizes by calling lots of accounts that have very big code sizes. The block hashes, I mean, calling the storage and accessing storage may even like make the witnesses slightly longer potentially than if you construct the witnesses with the hashes, but a bit more powerful in the like ability to verify against the state root. You don't have this like awkwardness of having some kind of set of hashes that you don't verify without having the full headers.
Okay, great. Thanks a bunch.
Thank you, William. Now moving on to the next section, it's not so very technical, like a little non-technical, but related to the EIP and the process, taking a little tangent on the EIP. about the recent article that is published by you, Tomasz. I know that you're not only a developer, but a researcher in the space, and you keep sharing your thoughts. So last Friday, there was an article on the life of EIPs, which is a good read on the process part. Can you share your thoughts a little bit more from the article with our audience, and also about the expectation with the network upgrade process?
Yeah, I mean, like, just thinking that probably I wouldn't call myself a researcher here, but I was like looking at this space of EIPs for sure. So I think I'll try to use this example for visualization of that process that is a bit more EIP specific. So in this article of Life of EIP, what I was trying to suggest is we had a discussion in the past about EIP-centric upgrades, network upgrades, where we, instead of collecting a few EIPs into the next network upgrade and bundling them together, testing them together, and creating that like every few months, we were thinking of a solution where each EIP separately can be approved, and when it's approved and tested, then it can be pushed to mainnet through testnet independently of all the others. And the EIP-centric solution had maybe had a bit of, it wasn't fully described of how exactly we test this EIP-specific upgrades, how we create testnets for those. But recently we started creating those testnets for EIP-2935, where 2 or 3 clients were having ability to synchronize together a network that was specifically designed for testing EIP-1559. And what do I mean by specifically designed? That's the network was defined as EIP-1559 enabled, and this is obvious, but it also had a tool for generating transactions that specifically addressed various test scenarios of EIP-1559, so various gas costs, gas prices, and so on. Now, in this EIP-centric solution with EIP testnets, for any EIP that arrives, as it would be 2935, a proposer or community or whoever is championing the EIP, they would have to convince 2 of the clients or 3 of the clients, depending on the threshold, but I think 2 would be sensible in the current state. If you have 2 clients that implement it and can synchronize a network that you define for them as the like Genesis file or chain spec, and if you can provide a tool that generates transactions that verify the behavior of this particular EIP, then you provide the client implementers with a very strong testing tool, because not only there are test scenarios, but also they show you that they can synchronize with some other client implementer. And now, not only the testing, but also immediately it creates arena for the community, for researchers, for Ethereum users to actually download those clients and the branches and just experiment themselves with this particular EIP. And it means that you can test various behaviors. You can give it to researchers of the economics of the network, to the security researchers, and so on for the initial scanning and reviewing. And then only then you can actually say, okay, so it's implemented into clients, it tested, and so on. So you can bring it to the all-core devs. And then on the all-core devs channel, you can say, oh yeah, okay, so here are the problems with it, and here are already some answers. We can ask, if we have some new ideas, we can continue researching it on those testnets that we designed. But if everything is fine, then you just, the next step is implement it in other clients and potentially design the gas costs, because you already have it running, so you know how much it costs, and then push it to testnet if you're happy. But it can be quite independent, and at the same time, you don't have this strange thing that now you would like to make the EIPs independent, but because they're always bundled with lots of other EIPs that are being tested, then you don't really have a testnet to make them properly verified before they go to mainnet. Yeah, so in the case of 2935, you could create a 2935 testnet that would store those block hashes and would allow people to deploy some contracts that already use that, play with that, synchronize in the clients, launch the network, and only then it could be pushed to mainnet.
Great, thank you. I mean, Peep and EIP is about improvement proposals, and personally, I am also involved with the Ethereum process, the EIP group, and there we are discussing about the network upgrade process, that how process should look like. It is very much similar to what you have tried to describe in the article, and I think I can share my views here. In parts, I also agree to the idea of shipping as proposal is ready, because that's the core theme of having an EIP-centric upgrade. However, the frequency, we are not very sure of that, like what it will bring for the node operators, like if it is too much for them to be upgrading very frequently or what. So we, the cat herders, are also conducting a survey on the node operators to collect data to understand the feasibility of this proposal. And nevertheless, this is a very good read for people out there. Must give it a read. And also, if you are running an Ethereum node, share your feedback with us. I will leave the link for this article as well as for the survey in the description section below. So my next question to you, Tomasz, is about your experience as an EIP editor. I'm not sure if this is your first EIP that you are championing.
Yeah, it's the first time I'm taking that role.
Okay, I mean, because when we are talking about a proposal or a champion, especially for the core proposals, it already comes with a lot of complexities of client's agreement to implement and push it through the network upgrade. What has been your experience so far leading this proposal?
I don't think I have enough experience to actually share something more here. Well, it's the first time I'm acting here as a champion of this particular EIP. So I implemented it, I understand it. I didn't yet create a bigger discussion. I hope this is the start of a potentially bigger discussion. And yeah, I mean, like, so it's too early to talk about experience. We'll see in a few weeks or in a month. Hopefully, I would say we'll see in 2 days when it's already implemented by everyone. But I don't think it will happen.
Great, thank you. So yeah, I think I am good on my part. Brent, do you have any questions for Tomasz?
Yeah, I had one question. I'm not technical like you guys. It's fun to listen to you guys talk. But I always assumed it was a fairly easy task to prove that any particular address, to prove a balance at any block since Genesis. But something you said almost made me think that that wouldn't be possible without 2935 or something like that, because we're working on a historical voting mechanism that will allow people to vote their ether at points of time in the past, not just current. But anyway, yeah. Will 2935 be required to prove address has a balance at any block since Genesis?
Yes. So if you want to verify the balance of an address from the past, then you would need 2935 if you want to ask about blocks beyond 256 blocks in the recent history. And you'll never be able to ask about that balance from before the fork, before the network upgrade that includes this EIP-2935. Because so far we are not planning to feed the historical hashes. It's possible, but I think it would be not very nice to do that. So most likely you won't do that.
Ouch, that makes this very critical for our stuff. So how do I sign up and say, yay, vote for this?
I think that's why I say that people probably don't appreciate how powerful it is, how many cool. I'm quite sure there will be lots of products that will appear in the space, in DeFi, as you showed on some voting solution, that will be enabled by this EIP. So I really like it, and I think it's simple enough to bring that, and there'll be some creativity from people. What you say, like, it is possible to verify outside of the of the EVM, like with the data from Ethereum chain. You have to download all the headers, and then you can verify all the historical states. And then when you do that, you can potentially like sign it with a group of voters that they validated it or something. But if you want to do all of that on chain, then you won't be able to do that without 2935.
Well, yeah, one of the possibilities is we would have a server that would download the entire chain and just store the addresses or how much ether was at every address. And then once someone signed and proved that they owned that address, then they would count that ether for that vote at that time and stuff like that, if that makes sense.
Yeah, so this is the only solution nowadays, but obviously it's not like you have to introduce some trust for someone from outside of the chain that they actually don't deliver the incorrect data. With 2935, you can verify it inside the EVM. I'm not saying it will be super cheap, but it should be relatively cheap. I think it should be around 20,000-30,000 gas for verification of the account balance. I'm not sure. I've never tested the cost in gas of the proof verification of the account balance, but I don't think it should be too hard. It's a few RLPs. Yeah, a bit of data, so maybe 50,000 gas.
Okay, cool. Thank you so much.
Welcome.
Cool. So recently in one of the core devs meetings, a list of proposals was released that was considered for YOLO V2 and V3 that may eventually be deployed in Berlin upgrade. So this EIP could not get into that list. My understanding was that there wasn't enough information around. I hope after this episode, it may get on the list, but that's not on me. It's on the core devs to decide. We thank you so very much, Tomasz, to join us today on Peep and EIP and talk about this proposal.
Right, thank you so much for allowing me to talk to people and preparing all of that, and probably also there'll be some more work from you to actually distribute that. So upfront, thank you so much for that. It's massive help to promote it, and it's like almost feel like you're more of a champion here, like you did the work. Thank you for that.
Thank you for your kind words. For people watching us on YouTube, you may find Twitter handle of Tomasz and rest of the participants of this meeting in the description section below. You will also find the link of the EIP and the presentation and everything that was discussed here. I mean, like not the code part, but yes, you'll find the relevant links in the description. If you have any questions, comments, and concerns about this or any other proposal, or if you have a suggestion or which proposal should be included in the next episode, please leave a comment. If you like it, share it with other community members. Let them know about the Peep and EIP. This is the first EIP focus series. We tend to keep it going with a lot of proposals to be discussed in upcoming episodes. Do like, share, and subscribe to Ethereum Cat Herders. Thank you, everyone.
Thank you.